we can start. And it's my pleasure to introduce the first speaker this evening or this morning for China. So it's Weinan E. He's professor at the Department of Mathematics in Princeton, and he's also director at the Beijing Institute of Big Data Research. He is, of course, well-known expert on many topics, in particular multi-scale modeling, stochastic PDEs, and more recently on machine learning and application to scientific computing. And among his many awards, I'll here mention the Theodor Karman Prize from Siam in 2014. And he also received the Peter Henrici Prize from Siam and ETH in 2019. And he has written a large number of scientific papers, including also a book on principle of multi-scale modeling by Cambridge University Press. So today, I'm very happy to introduce him, and his talk will be on machine learning and PDEs. Welcome, Weinan.
Thank you very much, Roberto. Thank you for the introduction, and thank you for the invitation. This is one of the few workshops on mathematics and machine learning. I think it's very important and very timely. Unfortunately, I have to miss most of the talks because I go to bed early, and then most of the talks after my bedtime. Okay, so I'll talk about machine learning PDEs, but I'll watch the videos afterwards. So I'll talk about machine learning PDEs, and I'll speak about two main topics in particular. One is regularity theory, new regularity theory that's required for high-dimensional PDEs. And second is PDEs that arise from continuous formulation of the machine learning. So let me start with machine learning. What is machine learning? Very briefly, let's think about this the simplest problem in machine learning, which is called supervised learning. We are interested in approximating some unknown target function f star. We're giving a finite piece of data, namely f star at finite number of values, n values. And we need to use these n values to find a good approximation to f star. So machine learning is a set of models and tools, algorithms for solving this problem and similar problems. So here we're talking about approximating a function, but there are also issues about approximating probability distributions, dynamical systems, and even solutions of differential and difference equations. What makes machine learning particularly attractive is that this set of tools are particularly effective in higher dimension. And roughly speaking, you can think of neural networks and similar models, not just neural networks, similar models as being the replacement of polynomials in high dimension. So polynomials are not very effective in high dimension. Polynomials or piecewise polynomials are not very effective in high dimension. They suffer from the so-called curse of dimensionality, which are discussed below. But neural networks seem to be a very effective replacement. So this is the general idea. Give an example, a very typical example of what machine learning can do. This is a well-known CIFAR-10 data set. We're given a set of images, and each image contains something. And something, one of the 10 categories of things, which could be cats, deers, dogs, frogs, and stuff like that. You're supposed to learn a function which maps each image to its category, so the content. Each image can be considered as a point in a 32 by 32 by 3-dimensional space. 32 by 32, that's number of pixels, and 3, that's the dimension over the color space. So each image is a point in the 3072-dimensional space, and we're supposed to find a function defined on that space. So this is approximating a function, even though the function value is discrete, only takes 10 values, but it's still approximating a very high-dimensional function. Let me give you an example which is very close to what we usually do, namely computing solutions of PDEs. Here we have a nonlinear parabolic PDE. I formulate this PDE as a terminal value problem because we're going to use the connection to backwards stochastic differential equations as the basic tool. But it's just reversing the time. So this is the same thing as computing. The usual way usually think of computing initial solutions of initial value problem. So here we are given terminal value. We want to compute, say, solution at t equal to 0. In order to solve this problem in very, very high dimensions, thousands of dimensions, we first reformulate the problem as a stochastic optimization problem. So I claim that this PDE problem is equivalent to the following optimization problem. We're optimizing, so we have the constraints here is a set of stochastic differential equations with 3 unknowns, x, y, and z, but only 2 equations. Notice that, only 2 equations, but still you can show that this set of equations, BSDs, the solutions are unique, exist in unique under Lipschitz conditions. The catch is that there is a measurability condition. So z is almost like the Lagrange multiplier for the constraint that the process has to be adapted. Anyway, subject to this dynamic constraint, we're minimizing the expected value of the difference between the terminal value of y and the terminal value of and the terminal condition. One can show the equivalence is given by the following: that the solution, the solution of this BSDE is given by the solution of the PDE via this relation here. Okay, so using this, since we have reformulated this as a stochastic optimization problem, so then it's easier to develop a deep learning based algorithm to solve this stochastic optimization problem. And this is what we call the deep BSDE method that's developed in these 2 papers. These are the first papers that started to solve PDEs in very, very high dimension using deep learning. So these are the ideas. I don't want to go through the details of these ideas. You can look at the paper if you're interested. The main point is that with this reformulation and with this algorithm, we can actually solve PDEs in very high dimensions. So here's an example of solving PDEs in 100 dimension. And this particular example comes from the stochastic control problem, this so-called linear quadratic Gaussian control, where lambda is the parameter, m is the control, and this is the white noise. We want to optimize this cost function, where this is the running cost, terminal cost. So one can write down the Hamilton-Jacobi-Bellman equation for the stochastic control problem, which is this, and we all know there's a Hopf transformation. Using that, we can write down the exact solution to this particular PDE, and we can use this exact solution to calibrate the deep BSDE method, and that's shown here. So the red is the solution, is the result of evaluating this expression, and the green is the result of deep BSDE method. And horizontal axis is the value of the lambda. Well, so these kinds of, so let me maybe give another example. This is a nonlinear Black-Scholes equation. Nonlinear because we're using nonlinearity to model the so-called, for example, default risk. So this is a model proposed by Daffy. They were solving this equation for in 5 dimensions in this particular paper. Here we are solving this equation again in 100 dimension, and you can see that the result converges quite nicely. Incidentally, we also developed another algorithm called multi-level Beguy iteration. So, and that for that algorithm, we have shown, accurate error estimates. So we can use that algorithm to calibrate the solution, and the error is quite small. So this set of ideas has been picked up very quickly by people in Wall Street, and it's now claimed to be used to price basket options, all kinds of interest rate dependent options, exotic options, which I don't quite understand very well. But for us, the important question is the following. The fact that we can solve these very high dimensional PDEs, so I gave an example of the 100 dimension, but now it's not just 100 dimensions, you can solve it thousands of, maybe even tens of thousands of dimensions. The fact we can solve these very high dimensional PDEs means that their solutions must have low complexity, cannot be too complicated. If it's too complicated, we cannot, we won't be able to do it, even though there are functions in high dimension. So the question is, how can we characterize this low complexity? Well, the intuitive answer is that they can be approximated easily. Again, the question is, how do we quantify this? So this is the first issue I'd like to sort of try to address. So let's go back to the classical viewpoint. The classical viewpoint about regularity, classically we characterize complexity of solutions of functions by its regularity, and then we have a very well developed theory of numerical analysis of how do we solve PDEs, the order of the accuracy, the approximation, the convergence rate, and stuff like that. So it's divided. The whole thing is divided into maybe three components. The first component is regularity from the viewpoint of approximation theory. So for us in numerical analysis, we view regularity as a measure of the complexity of approximating target functions using simple functions, namely piecewise polynomials. So this would be a typical result. Consider a target function U star, and UH is some sort of a piecewise linear approximation of U star. And then we have these kind of error estimates where where we say that, let's go back. Then the classical approximation theory claims that this kind of estimates holds if and only if the target function is in some sublet space, or approximately, maybe Bessel space. This is for alpha less than 1 or 2. And the convergence, so the rate of convergence is related to the degree of irregularity for the function. So this is what approximation theory tells us. The bigger the alpha, the easier it is to approximate U star. So the regularity characterizes the degree of difficulty for approximating this function. So that's the first part, just the approximation theory. The second part is regularity theory of PDEs. So we ask whether the solution of a certain PDE belongs to a particular sublet space or Bessel space. The third part is analyzing numerical algorithms. So we say finite difference or finite element methods. Then the conclusions are that there is certain convergence rate, and the convergence rate depends on the order of the method and also depends on the regularity of the solution. So this is the classical picture. Basically, we want to redo this picture in high dimension. So why doesn't this picture work in high dimension? That's because of the curse of dimensionality. Now, here, if I measure the error in terms of M would be the total number of parameters, not the mesh size H. Then the accuracy would be given by this. And you notice that there's a D. D is the dimensionality in the exponent, and that's the curse of dimensionality. So if you want to reduce the error to epsilon, how many parameters do we need? Well, that's the number of parameters. If you take the simple situation where alpha is equal to 1, epsilon equal to 0.1, then the number of parameters is 10 to the D. And if D is 3,000, this is a huge number. That's the classical curse of dimensionality problem. It's not just that, there are increasing evidence that Sobolev and Bessel regularity, or Lipschitz or C alpha, these kinds of regularity, measuring regularity by measuring complexity by the number of derivatives is not a good idea in high dimension. This function class is just too large. And also grid-based algorithms, such as finite difference and finite elements, don't work in high dimension. So, so this is where machine learning can help in practice, and this is where we want a new theory. So I call this a modern approach. It's not very complete yet, but the idea is that we want to have a approximation theory that's independent of dimension. So we want approximation results of the following type, where the error is bounded by something which depends on the target function, and the convergence rate where alpha is independent of dimensionality. So we want theorems of this type. And then if we have theorems of this type, the next step would be to say, okay, given a PDE, does the solution satisfy the following condition? Namely, this particular norm or pseudo norm is finite for that particular PD. So this will be the regularity theory, corresponding regularity theory in high dimension. So what should be the value of alpha that we expect in here? But to answer that question, let's look at the one situation for which we have good understanding in high dimension, namely computing integrals, computing expectations. So if we want to compute this expectation, we can do grid-based algorithm like Simpson's rule or trapezoidal rule. Then you would still suffer from curse of dimensionality. But we can also do Monte Carlo. This will be Monte Carlo. We're just sampling, take an ID sample of the particular probability distribution of mu and approximate this expectation by this empirical sum. Then the error satisfies this exact relation. So this relation is exact. The error, the variance of the error, of second moment of the error, is the variance divided by m. There's no 1 over d in the exponent. So this is the kind of results that we like. We like to, here we're addressing a simple problem, namely computing integrals. We would like to have something similar, but for a harder problem, namely approximating functions. So the question is whether, can this be true? And if it is true, what would be the definition of gamma? So let me give you two examples. The first example is so-called random feature model. So here is the setup for the random feature model. Phi is a collection of functions depending on the random variable W. Pi is the probability distribution for the random variable W. So we call this function phi parameterized by W. The hypothesis space, which is just the space we use to approximate our target function or trial function space. In finite elements or Galerkin method, we will call trial function space. In machine learning, we typically call hypothesis space. So hypothesis space for the random feature model is defined as follows. We take a particular ID sample of W, that's this Wj, altogether we have m features, and we form this linear combination of the random features. So this is the hypothesis space. Okay, so now, given this hypothesis space, we want to use this hypothesis space to approximate our target function. And so we want to develop an approximation theory for this particular hypothesis space. In order to do that, let's define this function space. So this function space consists of functions which admit this particular representation. Namely, there is some function a of W such that the function admits this representation. Now, this may look a bit strange beforehand, but I'll mention right away that this is very much related to the reproducing kernel Hilbert space. But before we do that, okay, let's say that we consider the functions that has this representation can obviously be written as an expectation. If this is true, let's define the following norm. So the FP norm of function f is defined as the pth order moment of the function a. I should put an infimum here because the a may not be unique. So then we take infimum over all possible a for which this representation holds. Okay, this is nothing but the LP extension of the reproducing kernel Hilbert space with this particular kernel. So reproducing kernel Hilbert space are very naturally associated with random feature models. Given a set of random features, we can define this kernel. And obviously this kernel is symmetric positive definite. Therefore, we can define the reproducing kernel Hilbert space associated with this kernel. The L2 norm, if P is equal to 2, the L2 norm would be the same as the norm in this reproducing kernel Hilbert space. So this is the LP extension of this LP reproducing kernel Hilbert space. The reason we define the LP extension of the space is that with that definition, with that extension, we can prove direct and inverse approximation theorem. The direct theorem says the following: if the F infinity norm of F star is finite, then for any small parameter delta with a probability at least 1 minus delta over the random sampling of the random features, there exists an A such that this is true. Namely, the target function can be approximated by that particular random feature model with an convergence rate, which is what we wanted, except for this logarithm or 2 over delta term. Moreover, the coefficients also satisfies this bound. The first remark is that this particular form of approximation theory, namely the deltas, and 1 minus delta, probability of 1 minus delta, and the logarithm. So this is a typical of high dimension. These are results of the concentration inequality. So this is what we want to expect. The kind of approximation theorems we want to expect. And then conversely, suppose we have a target function F star, and that target function can be approximated by some random feature model, and with some bounds, uniform bounds, the coefficients are bounded, then that target function must be in F infinity, or the F infinity norm must be finite. And this function must admit representations of this form. So these theorems are not hard to prove. So this would be the approximation theory for the random feature model. The random feature model is a linear model. If you look at, this is the linear hypothesis space, it's a linear model. Let me consider an example of a nonlinear model, namely two-layer neural network model. Okay, so two-layer neural network model looks very much like random feature model, except the W here is also parameters. They're also allowed to change. Before, the W's were fixed. Here, we can also allow the W to change. So the parameters are both the coefficients and the interior parameter W. Now, we want to develop, this is going to be our hypothesis space now. We want to develop a similar approximation theory for this particular hypothesis space. In order to do that, we consider functions which admit this particular representation. You can think of this as the continuum analog of this, or you can think of this as the analog of this representation here for the two-layer neural network. For these, we're going to ask, obviously one question is what kind of functions admit this representation? We're going to answer that question later. But for this kind of functions, we define a Barron norm, okay, which is like, a generalized mixed moment norm. If a function has finite Barron norm, we call that Barron function, and we define this to be the Barron space. Okay, the reason we call this Barron space, Barron function, Barron norm is that Barron started from 1993, started to think about these kinds of issues. Although the way he defined his space and the way he defined his norm is different from ours. This has actually caused a bit of a confusion, so which I'm going to address now. So first question is, what kinds of functions admit this representation, this particular representation? There is a theorem proved by Barron and Klosowski. Klosowski was Barron's student at the time, which says the following: that if the Fourier transform of a function decays sufficiently fast, such that this integral is finite, then this function admits representations of this type. Furthermore, the Barron norm, actually, this is another definition of Barron norm. By the way, I think I didn't say this. In the sigma here is the Relu function. I didn't say this. Sigma here is the Relu activation function. If you have an activation function which is not Relu, you can also define the analog of Barron space, but then there will be different LP Barron spaces. So here you notice that, this is like an L2 norm, and here I'm writing like an L1 norm. I didn't say, but all these different LP norms are equivalent. If the activation function is ReLU. But if the activation function is not ReLU, we would have to define different LP versions of Barron space. And I'm not going to talk about that, but there's a paper by some of my students and the collaborators on this. my students, actually. Okay, so the Barron norm is also bounded by this norm. So this was the norm that Barron created and Barron used. As a matter of fact, in the 1993 paper, he used it. The 2 was replaced by 1. Anyway, so we call this Barron's spectral norm because it's defined, it depends on the Fourier transform. It's different from the Barron norm that we defined. Now, the reason we don't like, we were not satisfied with Barron's spectral norm is that it clearly depends on dimensionality. The condition that this integral be finite clearly depends on dimensionality. We want to have something which is, at least, we hope it's dimension free, but we're not entirely sure, but at least it's not obviously dimension dependent. So and also you can well, maybe I shouldn't say this. What I was going to say that one can actually calculate this norm and in practical situations, and you can see that this norm is not big. It's far smaller than this norm. Now, okay, so this is, as I said, well, this is the theorem of Barron and Kolosowski, but we're not quite satisfied because the condition is dimension dependent. So we need more sort of results of this type. Let me mention another result, which is the singular set for Barron's function. This is a theorem proved by my postdoc, Stefan Wachowski and myself, which says the following, that we know that Barron functions are Lipschitz, but it's not necessarily C1. The set on which it fails to be differentiable is called its singular set. Now one can show Barron functions have the following decomposition, namely it can be decomposed as a countable set of functions, countable sum of functions, each of which the singular set is a low-dimensional affine subspace. So each singular set can only be a affine subspace. In particular, if you consider the following function, namely distance to the unit sphere, this function is not Barron because the singular set is the unit sphere. Unit sphere is not the countable union of affine subspaces of Rn, Rd. The distance to the origin, namely the L2 norm, is a Barron function. Okay, so with this definition of Barron space, Barron function, Barron norms, one can prove direct and inverse approximation theorems. The direct approximation theorem is very much like before. I'm lazy here. I should have written, with all the deltas and logarithm deltas. I should have done that actually. And the inverse approximation theorem says roughly the same as before. Namely, if a function can be approximated by two-layer neural networks with some uniform bounds on the coefficients, then the function must be a Barron function, and in particular, must admit representations of this type. Okay, I give 2 examples, but there are more examples. So for example, the most popular neural network, deep neural network, is called residual network. I'm going to mention that later. For the residual neural network, we have defined something called flow-induced space, which is like the Barron space for two-layer neural networks. So with that definition, one can prove that there's direct and inverse approximation theorem. And for multi-layer neural networks, namely 3 layers, 4 layers, 5 layers, there is also a definition of something called multi-layer space, and that's defined by Wachowski and myself. For which one can prove theorems of this type. And in particular, as the number of layers grow, the spaces are becoming bigger and bigger, and norms are becoming smaller and smaller. So ResNet is, in some sense, the best because the error of the approximation is the smallest. So that's the regularity theory. The next question is, can we establish, sorry, that's an approximation theory. So the next question is, can we establish a regularity theory for this kind of function spaces? So some initial results, only some initial results, and we'll be considering Barron space. Let's consider this particularly simple PDE. And one can show, there's a little paper by Stefan and myself, one can show that the Barron norm of the solution can be bounded by the Barron norm of the right-hand side, as long as lambda is positive. Okay, so this can be proved for general reactivation functions, which has finite limits. So like sigmoid type of activation function. For ReLU, the analogous result is this. And that these got proved by simple formulas. But if lambda is 0, this wouldn't work. For Poisson equation, this wouldn't work. Just because of the Green's function, because the Green's function doesn't decay fast enough. For heat equation, one can decompose the solution as the homogeneous part depending on the initial condition, and the inhomogeneous part depending on the right-hand side. One can also prove these kinds of bounds. Namely, the Barron norm can be bounded by the various Barron norm of the right-hand side. Also, for this Hamilton-Jacobi equation, if we assume that initial condition is bounded, the support of the initial condition is contained in the interval beta plus and beta minus and beta plus, and it's a Barron function, then the solution, we cannot show that the solution is a Barron function, but we can show that the solution is in the multi-layer space corresponding to 3-layer neural networks with this kind of a bound. We don't know whether one can bound this, whether Barron norm can be bounded, but we know the 3-layer space norm can be bounded. So in other words, we know that the solution can be well approximated by 3-layer neural networks, but we don't know whether the solution can be well approximated by 2-layer neural networks. Okay, there's also a counterexample, this is a counterexample on a finite domain. So when we consider Poisson equation or this kind of equation on a finite domain, there's the unit ball with a boundary condition, which is the ReLU function, the simple ReLU function. Then the claim is that this function is not a Barron function in the closure of the ball. And this can be proved by using the structural theorem of the singular sets that I mentioned earlier. So in general, we don't know bounded domain, nice bounded domain like a unit ball, with what kind of sort of regularity theorems we can prove at this point. So let me now turn to the second part, namely PDEs that arise from continuous formulations of machine learning. So machine learning, so here the idea is that machine learning is very powerful. Neural network, deep learning is very powerful, but it's also very subtle. You have to work very hard to tune the parameters. Nowadays it's not so hard to tune parameters for supervised learning, but for other tasks like unsupervised learning or learning dynamical systems, it's still very difficult to tune the parameters to get nice performance. So why is that so? So we think, the one sort of suggestion is that, well, it's almost like solving ill-posed PDEs. Ill-posed PDEs sometimes you can solve, but it's very, very, very subtle. It's very, very fragile. You have to work very hard. And it's not stable, right? We all know. So maybe we can try to formulate machine learning as a better posed, well-posed problem. By well-posed, we don't know how to define well-posedness in this particular case, in this situation yet. But the rough idea is that the variational problem, namely minimizing the test error, that variational problem should be simple. You should have a simple landscape. So this is sort of the idea. Turns out, in order to do this, the key ingredient is how do we represent trial functions? So for example, we can represent trial functions as using Fourier transform. This is a very popular way of doing it. But this doesn't work in high dimension. Instead, we prefer this representation, where we simply replace d omega by pi of d omega, where pi is the probability distribution. So this is very much analogous to these kinds of representations I discussed earlier. So these kinds of representations, or maybe even closer to this representation, where this is like e to the I omega x. No, here. So this is this is the feature function here. So if we have a representation like this, then we'll see later that we can formulate very effective machine learning algorithms in high dimension. So besides representing functions, we also need to formulate a variational problem. We also want to formulate the variational problem as expectations, because then we can use stochastic gradient descent algorithms. So stochastic gradient descent algorithms relies on the fact that the objective function is an expectation. And then we can ask, how, for the optimization problem, we can also define gradient flows. So let me see how this, let's see how this works. So representation of trial function, we already discussed this. Representing functions as integral transforms. This is a more general integral transform, where sigma is the more general activation function, not just e to the I omega. Or we can even define more general feature functions, not just feature functions of this form, but more general feature functions. Okay, so this is one way to represent trial functions. We call this integral transformed representation. And the parameters here would be like, the probability distribution rho, or here it could be like A and pi. So A would be a function, pi would be a probability distribution. So this is one way. Another way to represent trial functions is to represent with the help of a flow. For example, we can define this flow where the right-hand side has the integral representation. And then once we solve this system of ODEs, then we just add up all the components, we get these trial functions. So in this case, the probability, the parameter would be this one parameter family of probability distributions rho tau, or or this pi tau. So this will be, we call this a flow-based representation. There may be other representations. If you can come up with other representations, as you'll see, that would lead to a brand new way of thinking about machine learning. Having defined the representation of trial functions, the next question is to formulate the variational problem. So here, well, the variational problem is quite simple. We just want to minimize the test error. The test error is this. This is just a test error. Okay, in analogy with physics, we think of it as a free energy. So let's say the function, trial function is represented this way. And then our objective is to minimize this test error. The question is, how do we do that? Well, we want to define a gradient flow in order to solve this minimization problem. Now, in this particular representation, there are two kinds of parameters, A and pi. Pi is special because pi is a probability distribution. So the gradient flow has to respect that constraint. A does not have this constraint, so we can just define the gradient flow in this following simple way. But for pi, we go through a more complicated procedure. We first define the variational derivative, then we can calculate this velocity, then we use this continuity equation to define the gradient flow. One can show several remarks. The first remark is that one can show, as long as the solutions are smooth, the solutions will stay to be a probability distribution. So pi is always going to be a probability distribution. This is the first remark. The second remark is that this is a very well-known recipe in physics for studying mass transport, where V would be the chemical potential, and this would be called the Fick's law. So this is a very well-known recipe in physics. The third remark is that this gradient flow is nothing but the gradient flow of this free energy under the Wasserstein metric, the Wasserstein 2 metric. So now where our machine learning problem has reduced to solving these kinds of PDEs. Obviously, the next thing to do is to discretize. So how do we discretize? The first thing is to discretize this population risk or test error into empirical risk or training error. And that's easy to do. We just use the finite piece of data we have. As a matter of fact, we can't compute this in practice because we don't know all the data. We don't know finite piece of data. So that gives us empirical risk or training error. So that's easy. And then the next question is how to discretize these PDEs. Well, they're not really PDEs because this has integrals. So these are integral differential equations. But how to discretize these? Well, in high dimension, the most effective algorithm is particle method, because this is the dynamic analog of Monte Carlo. If you think about filtering, one area where this is done is filtering. In filtering, there's particle filtering, and there's we don't talk about finite element filtering because filtering is typically done in high dimension. Finite element doesn't work in high dimension. But particle method works in high dimension. So that's why we have particle filters. There's also smooth particle method. For those of you who worked on fluid mechanics, this is the analog of vortex block method. And if you're interested in low dimension, for example, if you want to solve Navier-Stokes equation using machine learning, well, maybe you can do spectral method. You don't have to do particle method. So let's see how this works. So let's think about this representation. In that case, the differential equation is this. A very nice, elegant differential equation. Oh, by the way, this is also the differential equation that arises from so-called mean field limit. There's a very nice set of papers, by a different group of people 2 years ago, where they considered mean field, the continuum limit of the training dynamics for two-layer neural networks, and view each neuron as a particle. So this becomes an interacting particle system problem. In the case, as an interacting particle problem, it's a mean field problem because particles don't interact with each other directly. They interact with each other via the function that represents, the function that these particles represent. So this is a mean field situation. And the mean field limiting equation is exactly this equation. So here, we got this equation from this recipe here. But it also arises very naturally as the mean field equation. So now we want to discretize this equation using particle method. And the particle discretization is the following. Namely, we represent these probability distributions as empirical distributions centered on these particles. The dynamics of these PDE becomes the dynamics of the particles. Okay, so how do we define what's the dynamics of the particles? So let's, for notational convenience, let's use UJ to define the particles. And with this, each set of particles, one can define the function represented by the particles. And then with this particular function, you can calculate the population risk or the test error. And that's a function of the particles, of the positions of the particles. One can show that this PDE is exactly equivalent to this ODE, which is the gradient flow of the particles with respect to this particular energy function, which is exactly the test error. In other words, this PDE admits the following kinds of exact solutions, namely the solutions are point particles and the particle moves according to the gradient descent dynamics. And that gradient descent dynamics is exactly the gradient descent dynamics for two-layer neural networks. So we kind of recover two-layer neural network gradient flow by discretizing. So we kind of went the opposite way as the mean field limit. We first sort of got the continuous PDE, and from some physics recipe, and then we discretize, and we got the two-layer neural network. Whereas the mean field went the opposite way. The advantage of the continuous formulation is that it is also quite natural to do the continuous formulation for different other settings. For example, multi-layer neural networks, residual neural networks. If you consider the particle picture, it's harder to formulate the particle picture. For example, for resonance. So now the natural question is, what about convergence? Does this set of dynamics converge to global minimum? Oh, wait, I need to speed up. Does this converge to global minimum? Unfortunately, this is hard. Even though this is a nice optimal transport equation, unfortunately, it's hard because the energy is not displaced in the convex. So the results so far are quite limited, but one of the most important results is the following result of Gisèle-Barr, which says the following. Assume the initial condition is, roughly speaking, has full support. The exact condition is stated here. The support has to cover every direction. By the way, here we're assuming that the activation function is homogeneous or reloop, something like reloop. Assume initial condition has full support. Assume that the velocity potential converges to a nice limit. Then the limit has to be the global minimum, namely the population risk goes to 0. As a matter of fact, these two statements are equivalent. There are other technical conditions, more start conditions, stuff like that. So I'm not stating, but this is the most important result. So the result says that if there's convergence, there's always a convergence subsequence. But if the whole sequence converge, the rho t converge as t goes to infinity, then it has to converge to a global minimum as long as the initial condition has full support. Okay, so this is so far the most general result. There are special results in one dimensions, which let me just roughly mention. For example, if we consider representation of this type, then the PDE becomes this. If the target is uniform, then one can show global convergence because there's a nice Lyapunov function, which is just the entropy. But in general situations, there's local convergence. As long as the initial condition is close to the target in certain way, then there's local convergence. And this is approved by usual dynamical system kind of ideas. In the last 2 minutes, let me just mention this, discuss the topic of formulating machine learning as the optimal control problem. So in this setting, we're defining trial functions this way. We have this dynamical system and then add up all the components of the dynamical system. So this is how we define the trial function. We want to choose the controls are this one parameter family of probability distributions rho. And we want to find optimal control to minimize this population risk. So obviously this is the optimal control problem. As optimal control problem, one can write down the Pontryagin maximum principle, defining this Hamiltonian, and then Pontryagin maximum principle claims that the optimal solution satisfies these conditions, namely that the optimal control is the argmax of this expected Hamiltonian, and then the state and co-states satisfies the Hamiltonian system in a forward and backward equation. Now, as before, we can also ask how do you formulate gradient flow? To formulate gradient flow, one just have to replace this condition, the maximum principal condition, by a gradient flow condition. Okay, so, okay, if you're interested in the details, you can look at our paper, but this is rather actually straightforward. If we discretize this gradient flow using the simplest numerical algorithms that we discussed earlier, namely particle method here, forward Euler, backward Euler here, then you would recover the gradient flow for the ResNets, for this particular version of ResNets, residual neural networks. So this is the general spirit, namely we get this continuous formulation, but if we discretize it using particle method, then you recover the gradient descent dynamics, gradient gradient descent algorithm for some corresponding neural network model. So in a way, neural network models are very natural in this setting. But we don't, this is sort of the most popular kind of algorithms in deep learning, but we don't have to do that. We can formulate algorithms based on maximum principle. And this algorithm called method of successive approximation. And it also works reasonably well. And actually converges faster than stochastic gradient descent algorithm. So this is a comparison of the maximum principle based algorithm, MSA, with the popular versions of SGD. So this is Adam. This is the simplest SGD. This is Adagrad. For those of you who know about SGD for deep learning, Adam is the most popular version. And this is the MSA. You can see MSA converges faster, particularly for situations for this kind of initial condition, which are bad initial condition, namely large amplitude. I should mention that the wall clock is comparable, and for several reasons. One is that this has not been optimized. These guys have been optimized to death by many people. These guys have not been optimized. So there's still room for improvement. So the most important difference is one is this, one is this. One is this maximum condition, one is this gradient descent dynamics. Okay, this is my last page. So, having worked on machine learning for several years, I asked myself, what have we really learned from machine learning? So what the most important component of machine learning? Machine learning has all kinds of tricks. Dropout, batch normalization, these kinds of Adam, all kinds of tricks. But the most essential component of machine learning, I think, from a mathematical viewpoint, is the following thing, namely representing functions as expectations. I discussed this representation. I discussed this representation. This is what's behind two-layer neural networks. This is behind ResNets, residual neural networks. And I didn't say this. This is the representation for multi-layer neural networks. It's more complicated, so I didn't mention this. But it seems behind every sort of neural network algorithm, there is some expectation structure. And once with this expectation structure, one can formulate continuous formulations of machine learning, and then discretize using any of the favorite numerical algorithm we like. And I think this is a better way to understand machine learning. In particular, if you have another way to represent functions as expectations, then you have a brand new machine learning algorithm or formulation or model. And, and this is, in my opinion, a more intrinsic viewpoint of machine learning. So I'll stop my talk here. Thank you very much for your attention.
Right, thank you. Okay, well, so I have a number of questions that have been written down. So let me read one. We have 5 minutes for quick questions. So an attendee is asking, is there any advantage of using deep layers based on your theorems when compares to the just 2 layers neural networks?
The answer is yes, because the deeper the layers, the smaller the norm. So going deep is in some sense a variance reduction algorithm. That's the understanding so far. There could be other advantages. At least from the approximation theory viewpoint, so the deeper the layers, the smaller the norm. So the smaller the error, the approximation error.
Okay, thanks. Let me read another question. There are many other mesh-free methods. So if the functions have low complexity, would it be possible to use other mesh-free methods to solve the problem?
So for example, radio-based function, that's another possibility. So I think in principle, radio-based function, so the theory for radio-based function is, to me, it's confusing. I actually tried to look into it, but I didn't get a good. So I guess the answer should be that one needs to look at further. For example, one needs to look at radial basis functions as from the viewpoint that I presented here today. There might be other mesh-free methods that I don't know of, but I think it'd be nice if someone take a deeper look, or take another look at radial basis function using the viewpoint that we talked about here today. But so far, it doesn't seem, I didn't find these kind of results in the literature.
Okay, and well, let me say another quick question. Is there any particular reason on using L1 norms in the definition of the Barron norm? Can you
actually,
use
no. Actually, no. All these, so when the activation functions remove, all the LP norms are equivalent. So that can be proved very simple. There's a simple proof in our paper. But if the activation function is not removed, then L1 norm or different LP norms might be different. Okay, is there a particular reason for L1 norm? Well, it depends actually in there. L1 norm is good for the Radamard complexity, which I didn't talk about. Actually, a very important concept is Radamard complexity. So L1 norm is very naturally associated with try to bound the estimation error, which I didn't talk about either. But if you want to bound the approximation error, actually L1 norm is not the best. It should be L2 or even L-infinity.
Okay, unfortunately, there are many other questions, but I think time is up. We should leave a couple of minutes to pass to the next speaker. Thanks again, anyway.
Thank you very much. Thank you very much for your attention.